Hello everyone. In this video we are going to solve a problem from rigid body kinematics, and we are going to do velocity and acceleration analysis. So here we have this mechanism that has three rigid bodies, A, B, B, C, and the disk. And at the moment bar AB is rotating 10 radians per second counterclockwise. So this is like omega AB, and it also has an angular acceleration of 10 radians per second squared, which is also counterclockwise. The disk rolls on this curved surface with a radius of 3 meters. Other dimensions are given. Here we assume that the rolling is without slipping, and you want to find alpha of the disk and alpha of member BC. Okay, so as you know, when we want to do acceleration analysis and find alphas, in the formula that we have for acceleration analysis, which is A of any point, let's say, for example, if I write the formula for point B and A on rigid body AB, you write like A of B is equal to A of A plus the tangential relative acceleration, which is alpha AB cross R of B with respect to A, and then plus omega AB cross omega AB cross R of B with respect to A, the normal or the centripetal term. Right? And you clearly see if I want to find some alpha or I want to find some A's, I also need to know the omega of that member. So when I write this formula for member BC, if I want to find alpha BC, I also need to know omega of member BC, which I don't. Or if I want to write it for disk, find alpha of disk, I need omega of the disk, which I don't. So before I can do this, first I need to know what is omega of member BC and what is omega of the disk. If I don't know these two values, I cannot proceed. So before I can do acceleration analysis, first I need to do velocity analysis, then come here. Okay, so that's what we do first. Since the omegas are not known, we first find them by velocity analysis, then go to acceleration. So I'm not going to use this formula now. I'm going to apply this later. What I want to do at the moment is do velocity analysis. So first I say V of point B is equal to V of point A plus omega of AB cross R of B with respect to A. This is the general relative velocity formula for 2 points on a rigid body. Okay, now point A is a pinpoint, so the velocity of it is 0. Here we also use a traditional XYZ frame and Z out of the board toward you, like that. Then counterclockwise omega is going to be positive Z, and the magnitude of it is 10, so this is going to be positive 10K. R of B with respect to A, it connects A to B, so it is this vector. This is R of B with respect to A, which if you go from A to B, you need to move 1 meter to the right, 2 meters down. So it is going to be 1I, then minus 2 times J. If we carry out the cross product, I cross k cross j is negative I, so you're going to get negative 10I. And then k cross, well, I guess I made a mistake here. Sorry, that's I. K cross I is j, k cross j is negative I, but I have another negative, so that's positive 20 times I, and then k cross I is j, so it's going to be positive 10 J. Unit is meters per second. Is this right? Well, it should be if we did our cross products right, but you can always do a sanity check by looking at the direction of this speed. So it's both positive components, so it means the velocity has to be something like this, v of b. Both positive. Is that correct? Sure. Because b is rotating about a is pinned down, so velocity of b has to be perpendicular to this radial vector r of b with respect to a, and because it's counterclockwise, so it's going to be upward and to the right, so it should have positive I and positive j components of the velocity. So if by any chance you made a mistake and got one of these numbers right, like what about to do, you can always check, hey, it does not make sense with that direction of rotation. That v of b, the sign of the x component or the y component, is wrong. So now you clearly see that if I have both of these components positive, then it is completely right. Okay? So that's v of b. Now that you have v of b, you can go to member BC because you know velocity of one point in it. So now you can say v of c now is equal to v of b plus omega of member BC cross r of c with respect to b, where v of b you just found, so this guy is 20I plus 10j. Omega BC you do not know, it's an unknown, but there are two possible scenarios for omega BC. It's either counterclockwise or clockwise, right? It's counterclockwise like this or clockwise like that. That's all it can happen in this 2D problem. So it's either positive k or negative k. So here I go ahead and assume it's positive. Well, maybe my assumption is wrong, but it's okay. When we solve this problem, if my assumption was wrong, I end up with a negative number for omega BC. That tells me my initial assumption was wrong. So don't be afraid to make an assumption here. As long as the line of action is correct, whether it's positive k or negative, the solution of the problem will tell you by a sign whether it's positive or negative. So here I assume it's positive sign. What about r of c with respect to b? Well, I have that guy. That one is this vector. It goes from b to c. This is r of c with respect to b. And clearly this 3i. What do I know about point C? Well, nothing directly from member BC. There is nothing that I know about v of c. So I cannot write anything about v of c, but I know one thing about c, and that is c belongs also to the disk. So not only I can find velocity of c through member BC, I can also find it through the disk. It's a joint, it's a common point, an intersection point. So what I will do, I will call this contact point here point P, correct? And I also need this vector r of c with respect to P. P is the contact point between the disk and the ground. So I can also find velocity of c through P and the disk. So it is going to be v of P plus omega of PC, or the disk, cross r of c with respect to P. what is velocity of P? It is 0. Why? Because it is doing what? It is doing rolling on the surface, and when it says rolling, it has to say rolling what? Without slipping. If there is any slipping, then the velocity of the contact point is not going to be 0. But because of this, it means velocity of the contact point is 0. So I can write it that way. Omega of the disk, again, what is it? I don't know, but again, it has to be positive k or negative k, counterclockwise or clockwise. Here, again, I make an assumption. I say, well, I assume that it is positive k. Could it be negative? Yes, the solution will tell me. Okay, so like that. What is R of C with respect to P? As you can see, it's the radius upward, but how much is the radius? Well, you have to look at the dimensions. Here, the distance from the center to point P, this distance is 3 meters, is as much as the radius of the curved surface, but the distance from the pinpoint A, which is at the same horizontal level to point B, is 2 meters. So this distance that I need, and that's the radius of the disk, this is 1 meter. And it's upward, so it is going to be positive 1 times J. So now we carry out the cross products, and we have two scalar equations coming out of this vector equation, right? Because these two vectors, this guy here on the left and this one on the right, they are equal, which means their I components are equal and their J components are equal. So if we look at them, the I components on each side is what? On the left side, I have a 20 here, and then I have a K cross I, which is J, so that's it, 20. On this side, I have a K cross J, which is negative I, so you will get negative omega of the disk. And if you look at the J components, here I have a 10, as well as a K cross I, which is J, so it's going to be 3 omega BC, positive 3 omega BC. And on this side, there is nothing, right? You clearly see that's it. There is, that's I, that's 0, so that's it, that's 0. And clearly from here, you see that omega of the disk is going to be negative 20 radians per second, and negative, you know, negative means it is clockwise. And from this bottom one, omega BC is going to be negative 0.3 radians per second, or sorry, 3.3, right? 10 over 3, 3.33 radians per second. And negative again means that's also clockwise. So both of these members are going to go clockwise. This is how this member is going to rotate omega BC. And this is how this disk is going to rotate omega of the disk. And here I can do a little bit of cleaning, right? So that you see what we are talking about. So that's omega of the disk. Right, omega of the disk is clockwise. Omega of member BC is also clockwise. But omega of member AB is counterclockwise. So now that I have the omegas, now that I have my omegas and I got them, I write them up here. And I said this one was negative 20 and this one was negative 3.33. So now that I have omegas, now I can go and calculate what? Alphas. Now I can write my acceleration formulas. So here is the time to use the acceleration formula we just copied earlier. Again, I start from member AB, that I know everything about it, including alpha AB, omega AB, and A of point A. Well, point A is a stationary point. It has no acceleration. So A of A is 0. Alpha AB is given to me. It is, as you can see, it is 20 radians per second squared counterclockwise. So it's positive 20K. R of B with respect to A, we had it last time, right? It goes from A to B, so it's negative 2J plus 2I. So this vector here I have. By the way, in 2D problems, where R is in the plane and omega is out of the plane, instead of this double cross product that you see here, I can simplify this in general and write it as negative magnitude omega AB squared times R of B with respect to A. So if you simplify it, this is the result. Definitely it's a centripetal term. It's in the negative R of B with respect to A, so it's toward the center, and the magnitude of it is R omega squared. This simple formula that I have here, which is a scalar, because this is just a scalar omega AB squared, it's a magnitude. This scalar times product, instead of carrying out two cross product, this is only valid when the problem is 2D like this, or when you have cases like R and omega are 3D but they are perpendicular to each other, then you might have the chance. But in general, you cannot always go from here to here. In this case we can, so let's carry that one, makes life easier. So this magnitude omega is simply the number that we had, which is 10. And as I said, R of A with respect to B with respect to A, which I need, if you remember, it is 2I, correct? You go down to, or 1I minus 2J. So it is 1I, then minus 2J. This is this vector. So if we carry out the scalar times vector and add it to here, and carry out also this cross product of alpha cross R, so you have a K cross I, which is J, have a K cross J, which is negative I, but there is another negative, so you get positive I. And then you have also a scalar times I and J. So you have two I's and two J's in the total that you have to add together. Your I is going to be negative 100 here, and here it's going to be 40. So 20 times 2, the negatives would cancel from K cross J. So that's a 40, that's a minus 100, so you will get negative 60. And then your J component is K cross I, which is J, so that's a positive 20, and this is a positive 200, because there is a negative and there is another negative. So there's going to be positive 220J. So acceleration of B is negative 60I plus 220J. Okay, and the unit is meters per second squared. Now that I have A of B, it is time to go to member BC, because A of B is known, so I have acceleration of 1 point. Now I can go to another point, point C, which belongs to member BC. So now I say A of C equals A of B plus alpha of BC cross R of C with respect to B minus omega BC squared R of C with respect to B. Pay attention here that I use the same simplification that I did up here. Instead of the double cross product, I use magnitude squared times vector. A of B is known. I have it right here. Alpha of BC I do not know, but I know one thing about it. It has to be clockwise or counterclockwise like AB or disk. So it's either positive k or negative k. Again, like these omegas in the previous case, I make an assumption for them. I assume it's positive k, but it might turn out to be negative. That's okay. So here, I say this is alpha bc times k. Magnitude omega bc I found. I have that number now. You see, now I need the number I found in the previous step. This number. If I don't have it, I cannot proceed here. So that negative 3.33 now has to be squared here. And R of C with respect to B, also, if you look at it, it was 3I. Good. So now, does this lead to anywhere? No, because I don't know this alpha BC, and I also don't know anything about A of C. From member BC, there is no information about C. And AC has two components, an X and a Y. And here there is alpha. So in general, there are three scalars unknown here. And this is a vector equality. It gives me two scalar equations, one for I, one for J. So I will be down to two equations and three unknowns, which is impossible to solve. But remember, C belongs to also the disk. So I can find acceleration of C also through the disk. It's a common point, an intersection point. So I should say this is equal to, if I found it through what? If I found it through the disk. And for the disk, I can go with the point P, or I can go, yes, I can go with point P, or actually, since it's just rolling without slipping, I can directly find acceleration of C through the disk. So I don't even need point P, because since it belongs to the disk and the disk is rolling without slipping, correct? So it doesn't matter on what surface. If you are rolling without slipping and the radius is r, and angular velocity is omega, and angular acceleration is alpha, and this center point is C, you know the condition for rolling without slipping is what? That V of point C is r omega, or A of C is what? R times alpha, correct? So these are conditions for rolling without slipping in general, right? So here I can find A of C directly from disk and say, since this is going with alpha of the disk, and here I assume the alpha of the disk is either positive or negative, okay? So here, let's assume that alpha of the disk is negative. You have no mandatory thing to tell you whether when you want to assume something for alpha, you should always assume positive. No, if you want, you can assume it's negative. Or no, you can say, well, it's positive, so the center is going to the left. So it's completely up to you how you want to assume it. It's not going to change the final answer, right? I always say in my classes, the world does not care about our assumptions. Whatever assumption that you use, the solution is going to be the same. Omega, we showed it's negative, so there is no reason that I show omega of the disk to be positive. It is negative, it's clockwise. Alpha of the disk, it's up to me. It's completely up to me whether I want to consider it clockwise or counterclockwise. If you don't like it, I can consider it counterclockwise, positive. Again, there is no change. So here, let's say alpha of the disk is positive. Fine. If that's the case, then A of the C is going to be R alpha, but it is going to be to the left. But V of C is going to be to the right. So V of C is going to be R omega times I, but A of C is going to be negative R alpha times I, because it's in the left side, to the left side. So if I want to assume alpha of the disk is constant and counterclockwise, this is going to be negative R of the disk times alpha of the disk in the I direction. So R of the disk times alpha of the disk. And how much is R of the disk? We calculated it last time, if you remember, it was 1 meter. So this guy is simply 1. And this alpha is just a scalar that is unknown. So now if I look at my equation here, my equation has only 2 unknowns. One of them is alpha of the disk, the other one is alpha of member what? B, C. So there are 2 unknowns, and there are 2 equations, one from equality of i's, one from equality of j's. If you look, i's, again, I have the I component for AB, which is negative 60. Here I have k cross I, which is j, so that's not going to do anything. Here I have this number times I, so that's a number you have to consider. And it's negative 3.33 squared times 3. Right? So this number is already 10 over 3, so it's 100 over 9 times 3 is 100 over 3. And it's going to be negative. So negative 33.33. And or if we multiply it by 10, it's just like this. Although this number, you know, it has infinite number of decimals, so if I use 2 decimals to be more accurate, that's what I have. So here I need to add one more extra 3 here, and that's the I on the left side. The I on the right side, it's negative alpha of the disk, or 1 times alpha of the disk. If you look at j's on the left, I have a 220. Then I have k cross I, which is j, and so it's going to be plus 3 alpha bc. And there is no j here on the right side. It's like plus 0 times j. So it's equal to 0. And clearly from here, your alpha bc is going to be negative 220 divided by 3, which is going to be negative 73.33 radians per second squared. And negative means it's clockwise. And if I plug that now up into the top equation, or actually the top equation doesn't need it. Yes, it's just directly giving you alpha of the disk. Good. So alpha of the disk, typically there is an alpha CD, but in this case, there is none. So alpha of the disk is going to be 93.33 positive, which means it is counterclockwise. So yes, alpha of the disk is actually counterclockwise. Our assumption was right. But when we assume alpha of member BC was counterclockwise, it was wrong. It was counterclockwise, it was wrong. It is clockwise, it's negative. So these are your final answers. Okay, so hopefully this problem was useful to you. The important point was to do velocity analysis before we can do acceleration analysis. And if there is a point that I cannot find anything about it from one member, but that point is a joint point, a point that is common to 2 members, I try to find its velocity or acceleration from either members and then set them equal to give me enough equations to solve for my unknowns. Okay, at the end of the day, you need to have enough equations for the number of unknowns to have. And if you do, then you can solve anything like this example. Thank you so much for your attention. See you in my next solved dynamics problem.